Okay, some curve sketching examples. As promised, we're going to tie all the little pieces together here of curve sketching now. And we go back to essentially one that could have been handled in future previous courses and previous grades, but we'll go after an easy one to get warmed up here and get a reminder going of all the little pieces that go on here. So don't worry too much about the steps, remembering each of the individual steps at this point, because you're going to do so many of them that the choices I make here as far as what things to go after, that'll become very regimented. Just see if you can follow each thing I do for now, and then we'll come up with a nice acronym to remember everything that I'm going to do here. One thing I'm going to mention way off to the side here is I think you're going to find that as you do more of these, the very first thing to do is to go over and factor this thing if you can. You're going to want it factored at some point anyways, so having the factored version can be very convenient. This one's a really old style factoring actually. It's just a common factor, so I'm going to pull that common factor out of it right now. 8x squared minus 5x minus 20, okay? So that's just ready to go if I happen to need it. I'll leave that out and you'll get, as your experience level comes up, you'll see that having that is really handy. So here are the steps. Okay, first we want to analyze, is there any domain issues that we should worry about as we're doing the work on this thing? So first look and see, take a look at the function itself and see, is there anything that x values that I have to worry about here? Essentially, the two big things you're looking for is where the denominator is 0 and where you're finding square roots and negatives. We've seen lots of the denominator equals 0 thing, but maybe not so much of the square root negative thing, and we'll see a nice example of that in the next lesson. But for now, this one doesn't have any domain issues, so we don't have to worry about that as we're going through. And we'll see some examples. The next two examples we'll do in this lesson, one will have no domain issues, and another one will have some domain issues that we have to worry about. So we'll see, I'll get a flavor for that. So the next thing we want to get is the intercepts. That's an old idea. We've been able to find intercepts for a long time. So for y-intercept, set the x value to 0, which is pretty easy to do in this function. So I get a y equals 0. So I already got a y-intercept, sorry, an x-intercept. It's both, isn't it? Y-intercept and an x-intercept to deal with here. X-intercepts can be a little bit more work. For x-intercept, we'll set the y to 0. And that's where this factored version comes in. We sort of see that we want to get this factored version going. So I go 0 equals x cubed bracket 8x squared minus 5x minus 20. So the factored version handy here. So I get two zeros. I get x equals 0, or I get this big thing equal to 0. Now, in the interest of saving just a little bit of space on this particular solution, I'll leave out the steps of the quadratic formula. I'll leave that to you. That's sort of old news. That's a good exercise for you. If you're like, am I still good at the quadratic formula? Take a moment and really work through and make sure that your quadratic formula is right up to speed, because you really, that really should be old news by now. I get here x equals approximately 1.92, or x equals approximately, my other value I get here is negative 1.3. Now for my graphing, that is more than accurate enough to go ahead and build my graph. So I don't need any more than that. So I'll just make a note here. You're going to have to show your quadratic formula steps there. Okay. Asymptotes will be another thing we'll look at, and we saw a lot of that in advanced functions. And again, I put it in here. This one doesn't have any, but normally you'd be looking for them at this point, and this one has none. By the way, everything I've done so far is really just advanced functions work. I haven't done any calculus at all here. And so now here comes the calculus. What I want next is intervals of increase or decrease. And from that, I'm going to get max and mins. That's what's going to come out of here, is where are the max and mins, which are going to be really handy. That's what we couldn't do in advanced functions. So what are we going to do now? F prime. So f prime here, I get 40x to the 4th minus 20x cubed minus 60x squared. And so I'm going to factor that immediately. You're going to find that all the time. As soon as you get a function you want to do some work with here, you're immediately going to switch over to factoring. So I get 20x squared. And so that's what, 2x squared minus x minus 3. And then hopefully this sort of rings a bell. For critical numbers, these numbers that are potential max and mins, we set f prime equal to 0. So what I get is 0 equals 20x squared. Oh, I'm just going to go ahead and factor that thing. I know that's what's coming here. So what about 2x and x? Let's see, possibly a plus 1 and a minus 3. Yeah, that looks about right. Minus 3, oh, that's good. And so then my critical numbers, so x equals 0, x equals 3 halves, x equals -1. There's my 3 critical numbers that I want to use in my single derivative chart. So me personally, over the years, just an experience, I switched the order here just to remind myself what order these go in for the chart. I don't know if you ever made that mistake before. I just usually switch the list around after I found them, so I know what order to put them in. So my sections I need for my single derivative chart, I need x less than -1. I need between -1 and 0, between 0 and 3 halves, and greater than 3 halves. Those are the sections. Ooh, I don't want that to look like a negative, do I? Those are the sections of this graph. If you want, it's the intervals of this function that I want to look at and see what the derivative's doing in each of those sections. So here's my single derivative chart. Let me get all the pieces of that thing. It was 20x squared, a 2x minus 3, and an x plus 1. Then you come up with your test values. So I got like a -5 test value, and that's going to lead to like a positive, negative, negative. So this section is going to be positive in there. Between -1 and 0. Ooh, -0.5. So 20x squared, that's going to be positive, negative, but now a positive in here. So that section is going to be negative. Let me slow that down in case that's slipping past you there. So my test value that I chose for this section between 0 and 3 halves, I'm going to test a 1. And so if I'm testing 1, if I go 20 times 1 squared, that's going to be positive. 2 times 1 minus 3 is negative. And 1 plus 1 is positive. So I get another negative section here. Again, way back when, we got used of the idea that it was always go positive, negative, positive, negative. But it doesn't have to do that. This factor of x squared makes it that it doesn't switch signs at 0. So that's an interesting feature of the graph. And we'll see more about that coming up, what that means. And then x greater than 3 halves, well, that's easy to, use a test value of like 10. And then so 20 times 10 squared is like positive. 22 times 10 minus 3, that's positive and positive. So I get positive in this last section. So just to review what all that means, in a single derivative chart, that means I went from increasing to decreasing. And then it was more decreasing. And then increasing. So nothing there in the middle, and this is where I said we're going to find our max mins in all this, is that if we go from increasing to decreasing, then we've got a max at -1 comma something. And over here, I've got a min at 3 halves comma something. And where do I get the something? Well, I just take those x values and I sub them back into the original function and see what y values I get in. I sort of leave that as an exercise. Plug that in to make sure you get the y values I do. I get a y value of 7 when I take a -1 and sub it into the original function. And when I plug 3 halves in, I get like -32. And I got the fraction here of 1/16. That's what my calculator brought up on the screen. But hey, -32 in a little bit, that's going to be accurate enough for the graph we're going to do. Okay, so all of that is old news before this chapter. See, domain, intercepts, asymptotes. And you might be thinking, oh, well, you didn't really talk too much about asymptotes there. That's okay. I got other examples coming, but that was all from advanced functions, domain, intercepts, and asymptotes. But now in calculus, we learned about intervals of increase and decrease. Oh, maybe I'll just underline that. Just pretty that up a little bit. Intervals of increase and decrease, and so then we can find those max mins, and we could do that in previous chapters. So what's new here, the last step is concavity. That came from the last lesson. And so now we want to analyze the double derivative. So here the double derivative. Okay, where's my single derivative? Right there, 40x to the 4th. So now I get 160x cubed minus 60x squared minus 120x. I'm going to immediately factor that because I got to use this thing. So what was it? About a 20x that comes out of there. And so what's left over? 8x squared minus 3x minus 6. Okay, so I get x. So 4 points of inflection set f double prime equal to 0. So I get 0 equals 20x, 8x squared minus 3x minus 6. And boy, do yourself a huge favor here, again, with the quadratic formula. Make sure you're going through that and testing that out. It's easy to forget all the little steps that have to happen there, and make sure you're getting the same things I get as I got when I do the quadratic formula on that thing. I get x equals negative 0.7, and also x equals 1.07. Approximately. I rounded those off. You check that out to make sure you've got those. So out of this, I also get points. Oh, not yet. No points of inflection just yet, because I got to do my chart. But that's what I'm going to get out of this. That's what I'm aiming for, is getting the points of inflection. Now, to get those points of inflection, I'm going to have to go down here. I don't have enough space here, so I left some space down here to build a double derivative chart. Now, I'm going to be very careful with this one. Okay, the lowest x value I had was x of negative 0.7, so I need x less than negative 0.7. Then I need between negative 0.7 and 0. And then I need between 0 and, weirdly, 1.07. And then greater than 1.07. See, I used one that had some really awkward values to really show off how you handle those awkward values. Lots of the ones you'll see in the homework and so on aren't nearly that bad. So then I need my double derivative. What was my double derivative again? It had a 20x and this really awkward 8x squared minus 3x minus 6. It didn't break down to the individual factors. So then, boy, what a nightmare you got on your hands as far as checking this out. And you know what? Some people just give up on this. They just take their test values, and let me write some test values up on the top that you could use. Less than negative 0.7, say negative 2. Between negative 0.7 and 0, say negative 0.5. Between 0 and 1.07, positive 0.5. And then greater than 1.07, say like a 5. And they just sub it back into the f prime. Once they've got that quadratic number in there, and they know I got to sub into it anyways, they just take this negative 0.7 and sub it into the whole function. They don't even play around. So like this whole double derivative was 20x, 8x squared minus 3x minus 6. But maybe, just maybe, it's just easier to, once you got to deal with that, is just to go back to this 160x cubed, what was it, negative 60x squared, minus 120x. I'm going right back to the source there and just take my calculator and just punch my test values in there. And I know that's painful compared to some of the charts we have to build, but sometimes you're stuck in that situation where there's not much you can do but sub those in. So you have to play around with that and get used to how much subbing you're willing to do and how much, what work you're willing to do. I mean, you could put the negative 0.2 in the 20x and then also into this other part, but like I say, most people, once they know they have to sub it in and get their calculator to find a certain value, they just sub it into the whole thing there and just find their values that way. And if you do that, if you sub in negative 2 into that thing, you'll get a negative value. You sub your negative 0.5 in there, you'll get a positive value. And you sub your 0.5 in there, you should get a negative value. And then your 5 in there, and you should get a positive. Leave that as an exercise. Get yourself, back up to speed here. And I'm sort of unhappy with something I'm seeing here. This sort of looks like a 4 here, so I'm just going to fix it up while I'm still talking. There, that's better. So that's good practice to just get back in the swing of things as far as typing things into your calculator and so on. So what I get out of this is a bunch of points of inflection. this is a point of inflection at negative 0.7 comma something. And then here I've got a point of inflection at 0 comma something. That might be easier to sub into. And here, point of inflection at 1.07 comma something. So you take those x values and you go all the way back to the original function, and I get a 4.3 when I sub back in, I get a 0 when I sub back in, and this last one, when I sub it back in, I get like a negative 19.8 when I sub that back into the original function. Okay? So you can go through those steps and see if you get the same things that I do, subbing those things back in. Okay? Now, all the steps are done. Now we start putting these things on the graph. And as you gain more experience, you might find that, no, I actually want to put them on the graph as I go and get a feel for what's happening, and you can do that too. So let me switch over to a nice, let's say a nice blue color that we'll be able to see on the screen here. And I'm going to go right back to the beginning and go, okay, what do I got here? For y-intercepts at x equals 0, I found a y-intercept. I got that as the value there. Now, I don't want to get too far and talk about scale here because there's a big value here. My brain's screaming at me there's a big value. Oh yeah, here it is. Let me just highlight that thing. This big value of negative 32. Ooh, that was fun. Negative 32 sort of makes me think I got to build a giant scale here to sort of include that thing and fit it on my graph. So I'm not going to change the scale too much more than I have to here, but I've only got 2, 4, 6, 8, 10, 12, and I got to get down to 32. So that makes it I'm going to have to go, maybe 5, 10, 15, 20, 25, 30. Even that's not going to be enough. I like negative 10, negative 20, negative 30, something like that. And this is 10, 20, 30. Worse than that, these x values are like tiny, like 1.07s and so on. So this way I'm going to go 1, 2, 3. Now, if you're doing this on regular graph paper instead of like on a screen like this, you might be like, well, I got lots of space. I can just spread this out. I can use a whole sheet if I have to. What do I care? And that's absolutely true. This is only trouble because I'm trying to do it on a screen like this, right? Okay, so I'm ready for those big points now that are going to come up. What was the next thing? Okay, so I found the y-intercept is 0. X-intercepts, I found an x-intercept is 0. Oh, yeah, of course, same thing. Okay, and then 1.92, sort of like there. And then negative 1.3, sort of like there, okay? I've already got a really good idea what this thing's going to look like, but I've got other points now. I've got lots of other information, so I can get exactly what's going on here. My max mins, where were those? There was a max min. There was a max at negative 1 comma 7. So negative 1 comma 7 somewhere about there. And I'm going to label these points later, but for now I'm just going to get them on there. And then 3 halves, negative 32 and 1/16. So it's 1.5 and negative 32, something like about there. I'm going to label these points so it's obvious exactly where they are. Now finally, these points of inflection. There's one at negative 0.7 and 4.3, a very weird location. Negative 0.7 and 4.3, sort of like there. So this is going to really be weird when I go to do this, but I'll show you how we incorporate the points of inflection in a second. There's also a point of inflection at 0, 0. That's already on there. And then my last one, 1.07, and that was negative 9.8. You might be thinking, well, what if I don't get them exactly right? You know what, in graphs like this, we're not looking for exactness. Like there's 1.07, you might think, oh, actually, I think 1.07, if that's 1.25, maybe that's a little more left of that. We're not going to get too bent out of shape with these things. If it's between the right two grid lines, we're going to be pretty happy. I just want to add one little thing here that normally with the graphs we're used to would come under asymptotes, but because this is such a simple one, it's actually end behavior I want to talk about. I'm just going to put that at the end here. Every once in a while we do want the end behavior, and looking back, and there'll be examples coming up of end behavior where it's a horizontal asymptote or it's an oblique asymptote. There's lots of possibilities here, but reaching back to our advanced function skills, if we look at 8x to the 5th, that means we know that as x goes to negative infinity, the y will go to negative infinity. And as x goes to infinity, y will go to infinity. I'm trying to write that just like you saw it in advanced functions. But essentially, we sort of did this dance and we said, listen, if we've got a positive coefficient and an odd degree function, it's going to sort of end up like that, okay? So now to draw this thing, I've got all the information I need to draw it, but the only real weird part is the concavity. See, the first section of concavity says it's concave down. Let me write that in here. Concave down up till x is negative 0.7. So up to this point here. So when I draw this, I got to make sure I really go and say, okay, it's going to be concave down like that. Hopefully you can see that concave down. And then this is the hard part. And then it says concave up between negative 0.7 and 0. So then this part is going to be sort of curved upwards. So you sort of got to show that on there. Then concave down again. This really gets the shape of the graph. So now concave down into this point. Then concave up again. You see, this concavity is the final piece of the puzzle because it really shows you which way the graph is turning in each section. And away we go like that. Done. Well, sort of done. Let's just, I'm going to switch over to purple here to do my labeling. I'll label all these points because when I'm estimating points, when they land right on grid lines, it's not so bad if you leave it the odd label out, but you're really moving forward, want to label every single point on here. So I'm just going to put a little 0, 0 on there, and this one over here. I go in order from the algebra so I don't get confused. And then there's a 1.92 comma 0. And then negative 1.3 comma 0, here it is over here. And notice I put those on in a different color to really show them. We had a max at negative 1.7. And then we had a min at 3/2. Weirdly, 3/2 comma negative 32 and 1/16. Yeah, I went to the decimals in the other one, so you could have gone to the decimal on this one. It was just such a nice fraction that I used it. And then these points of inflection, I already got the 0, 0 on there, but then the other points of inflection were negative 0.7, comma 4.3. Ooh, that's awkward getting that in there. So sometimes you got to sort of write it underneath and put a little arrow up to it, something like that. And then 1.07, comma negative 19.8. Same thing. I'm just going to draw a little arrow in there. Maybe I'll just highlight the points a little bit so you can really see them. Okay. That's the first of the graphing examples. I'm going to end the video there so you can absorb that and then come right back for a second graphing example. I'm going to go after 5x over x squared plus 1.